Okay, in this lecture we're going to talk a little bit about the computer itself. So in the last lecture I said I'm not terribly interested in the computer. In my opinion, computers are the least interesting part of computer science. It's the software that controls the computer that is so interesting to me. However, in order to write programs, we do have to know something about what's inside the box. So, what is a computer? Well, a computer is a series of components that are connected to each other with wires, or more likely nowadays on a printed circuit board, which just embeds the wires in sheets of plastic. You've probably all seen these. They're little green boards with many different electronic components connected to them. By far the most important component is called the processor. Okay. The processor is made up of a few components itself. So we have this thing called an ALU, which is an arithmetic and logic unit, a control unit, and some registers. Okay, so let's talk about the ALU. Again, it's short for arithmetic and logic unit, and it handles obviously all the arithmetic and the logic. In this case, the logic means the comparing of numbers. So the processor can do addition, subtraction, multiplication, and division. The processor can also compare two numbers to see if they're equal, not equal, less than or equal to, greater than, and greater than or equal to. There's 6 comparison operations there. Okay, next we have the control unit, which is on the processor. The control unit handles the order that programmer-written instructions are executed by the processor. Okay, by default, all instructions are handled in top-down order. In other words, a programmer writes instructions in a file from top to bottom, and unless told otherwise, the processor will actually execute them from the top to the bottom. Okay, the order of execution of statements written by a programmer is called the flow of control. Okay, now I'm going to be talking a lot about the flow of control. Okay. There are a few ways to alter the flow of control. So I said by default, instructions are executed basically from the top down, and we call this the sequential flow of control. So just you might remember from the program in the last lecture, there was a main function, and things just got executed from the top to the bottom. That's called a sequential flow of control. However, there's a way to alter the sequential flow of control. You could use some conditional logic. And basically what that means is you come to a fork in the road and you choose one of two paths to execute. So remember when we compared the current number to the largest number so far? And if it was larger, we did one thing, and if it wasn't, we did something else? Okay, that's some conditional logic, where basically we ask the computer a question. Is something true or false? And if it's true, we're going to kind of start to execute these statements. And if that question that we ask turns out to be false, we'll do something else. We never do both. We always pick one or the other. And then eventually we go back to our normal sequential flow of control. So there's usually, 2 paths, although there can be more than 2. You take one of these paths, you never take them both. Okay, and we'll talk about conditional logic soon. Another way to alter the flow of control, the normal sequential top-down, is to use something called looping. So we might want to repeat a section of code repeatedly. So remember, we're going to do the exact same thing with each number that was said out loud. We're going to write it down in the box, compare it with the largest so far, and then maybe change largest so far. Okay, so that kind of looks like this, where you want to do something over and over again. So you do these sequential statements, and then you go back to this point, the starting point, and do them again and again and again until, again, usually we do some conditional check, and that determines when we should stop looping. Okay. So that's really good if we want to repeat statements over and over again, but we don't want to type them all, millions and millions of times. We just put the few statements in a loop, and they will repeatedly be executed. Okay, and the last way to alter the flow of control, the normal top-down flow of control, is to use something called a function. A function is just a named block of code that can be reused over and over again without the programmer having to type the statements over and over. So we might have this bit of code, right, and we might want to go down and jump to some function. Right, so maybe this function are all the statements that are used to find the square root of a number or something like that. Okay. And we might want to find the square root many times in a program. So rather than typing these statements over and over again, we put them in a named block. And then from up here, we can call that function. And the flow of control jumps down to the block. It does its thing. And then as soon as we are done with that block, the flow of control jumps right back to where we started. Okay, or right back where we called the function, and we pick up with our normal sequential flow of control. Okay, so almost all of this course is talking about these four things. We'll talk about if statements and whiles and functions, for the entire semester. Okay, so they're really important. So the control unit handles the flow of control. The next part of the processor that we'll talk about are the registers. And the registers are just a bank of memory cells that are right on the processor. So all data must travel to these registers in order for the processor to manipulate it. Okay, with, for example, the ALU. Right? So if we want to do some arithmetic, we first have to get the data inside the registers, and then we can transfer this data to different places like the RAM, which we'll talk about in a second. So RAM, or your system's memory, okay, the processor is connected by wires to the computer's memory, or RAM. So I'll use the terms memory and RAM interchangeably. They mean the same thing. Now in this picture it looks like there's just one wire that connects them, but in reality there might be 32 or 64 wires. And that partly determines whether your machine is a 32-bit machine or a 64-bit machine. Okay, the computer's memory can hold many bytes worth of data. And a byte is just a collection of 8 bits. And a bit is either a 1 or a 0. We'll talk more about bits and bytes in later classes. For the most part, we don't have to completely understand them right now. When I talk about numbers, I'm just going to write decimal numbers when I draw my pictures. But inside the computer, those numbers are really stored as these collection of bytes. So today we measure the amount of data that can be stored in a computer's memory in gigabytes, or billions of bytes. Okay, so that's a lot of bytes. There's a lot of room in memory to store data. Now, just a few years ago, we measured the size of a RAM in megabytes, or millions of bytes. And if you're really old, you might even remember a time when RAM was measured in kilobytes, or thousands of bytes. Okay, I have no doubt in the not-so-distant future we're going to be measuring our RAM in terabytes, or trillions of bytes. Okay, so our RAM can hold a lot of data. And that's the whole point of RAM, is to hold data. Remember when we talked about carving out room in our brains to hold the largest number so far in the current number? Well, the place where data can be stored in a computer is called the memory. Right? So the largest so far in the current number would be stored here in the RAM, or the memory. The processor might read a value from the memory and put it into a register. Then the processor might compare it with something, or perhaps do a little bit of arithmetic with it. And then the processor might write the new value from a register back into the same memory location where it was found. So there's definitely communication between the RAM and the processor. Now, the term RAM is short for Random Access Memory. And again, it's just another name for the computer's memory. It's called random access because it takes the exact same amount of time to read the first byte in RAM as it does any other byte. So recall that memory can hold a tremendous amount of data, and if you choose any random piece of data in the memory, it will take exactly the same amount of time to access it as any other piece of data. Okay, we'll see that this is not true with other storage devices like a hard drive. RAM is also volatile, which means that when you turn the power off on the computer, any data that was inside the RAM is going to be gone forever. And we'll also see that with other types of storage devices like a hard drive, that's not true. RAM is also very expensive per byte. And we'll see that that's not true with other storage devices like a hard drive. Okay, so when I talk about these other storage devices, I'm talking about auxiliary storage. Okay, so auxiliary storage is used to store data, just like RAM, but it has a few significant differences. Most computers, of course, have a hard drive to store data in files, and a hard drive is a perfect example of an auxiliary storage device. The difference between RAM and a hard drive are speed, so the amount of time it takes to access the data. The cost, when I talk about cost, I'm talking about the cost of bit, the cost per bit for the storage, per bit or per byte. And the volatility, whether the data is present or not. Whether the data is persistent or not. So when the power goes off, does the data go away or does it stay? Okay, so let's kind of look at what a hard drive looks like. Okay. Hard drive is this disk. Okay. It's a platter coated with magnetic material. And this platter spins, and an arm hovers over the platter. Okay, so there's this motion here. This guy's spinning, and we have this little mechanical arm that hovers over the platter. The arm can read whether there's a magnetic attraction or repulsion on the disk directly underneath the arm, and it treats these as equivalent to either a 1 or a 0, okay, or a bit. And as the disk spins, the arm can read the bits that are directly underneath it. A couple of notes about the speed that data can be read from the disk. There's a delay in waiting for the arm to move to the correct position on the disk, and we call this the seek time. So maybe the piece of data that we want to read is way over here, and what that means is we'd have to move the arm in this direction so that the head is right over that piece of data, because that's the only time it can read it. So we call that a seek time. Okay. There's another delay in waiting for the disk to spin underneath the arm once the arm is in the correct position, and we call this a rotational delay. So maybe the arm is right here, but now we have to wait for the disk to spin. If we want to read this piece of data, we have to wait for the disk to spin to get right under the arm. Okay. That's a rotational delay. Okay, and these things add up to make it very expensive to read from the disk. Okay. The disk and the arm move really quite slowly. Okay, so let's compare this with RAM. Okay. RAM has no moving parts. Okay. If we were to look at a RAM, okay, or a memory, the picture I want you to think of is this long series of boxes. So I talked about kind of carving out boxes to store data in the last video. Well, these boxes, okay, that's all a RAM is. It's this long series of boxes. And if you have, let's say, 8 gigabytes of RAM, you have about 8 billion individual boxes that you can store data in. Okay, to read some bits from the RAM, I talked about those wires earlier. So there might be 32 or 64 wires that feed into a RAM, and we call these the address lines. Okay, they feed into the RAM. And then we have another, again, either 32 or 64 wires that come out of it. We call these the data lines. Okay. So to read some bits from the RAM, an electrical signal is sent down some of the address lines, and after a very short amount of time after the RAM receives those electrical signals, some data comes out on the data lines. Okay. So we basically just kind of send an address in here. We wait a very short amount of time, and then the data inside one of the boxes will be sent out on the 32 or 64 wires that are coming out of the RAM. Okay, since there are no moving parts and the electrons move very quickly, when we talk about the amount of time it takes to read from a RAM, we're talking about times that approach the speed of light. Now, reading from a disk drive is just tremendously slow compared to reading from RAM. Okay, why? Because we have all these moving parts. So yeah, we can make that disk spin pretty quickly. Maybe, even if we can get that disk to spin 30 times per second, we still have to wait for there's a rotational delay, there's the seek time. That's nowhere near on the same order as the speed of sending electrons down these wires. Okay, so when buying a computer, most people look at the processor speed and assume that's going to control how fast the computer will operate. In reality, the amount of RAM that you have is critically important to getting good performance. If you have a small amount of RAM, then the data your computer needs will more likely come from the disk. So the disk is used kind of like a RAM backup. When we run out of memory, the operating system will start putting data on the disk. If we use all of our RAM, then the computer will start to use that disk, and if the computer is going to the disk frequently, then your computer will slow to a crawl. Okay, so whenever I buy a computer, I always invest in lots of RAM. Okay. Now, having said that, disk drives are very cheap per bit. They have some advantages. They also maintain their data after the computer has been turned off. So it makes sense to have a very large hard drive to store data persistently, or in between power up and power downs. Okay, so it makes sense to have both a RAM and a hard drive. That's the main point I'm trying to make here. Again, RAM loses its value when the power is turned off. A hard drive doesn't. RAM is very expensive per bit. A hard drive is very cheap per bit. So these two things in combination makes a computer reasonably fast and reasonably affordable. If we just wanted to store all of our data in RAM, I suppose we could do that, but the computer would not cost $1,000. It would cost maybe $100,000. And that was just a trade-off we made so that everybody can have a computer on their desktop. Okay, the next piece of the puzzle here are the I/O devices, or the input and output devices. Examples of these include keyboards, monitors, mice, and several others. So I'm using a pen tablet to draw the pictures in this lecture. The pen tablet is an I/O device. And the I/O devices are how humans interact with the computer. Okay, so this entire picture, of course, is a simplification of reality, but it's good enough for now. Okay, in fact, programmers do not have to actively think about most of these components. When programming, the programmer only really has to think about the computer's memory, or RAM. Okay, so I'm gonna say this again here. While we're programming, really the only physical component we have to think about is the RAM, or the memory. And you can think of memory as this just really long series of boxes. Okay, and again, if you have 8 gigs of RAM, you have about 8 billion individual little boxes. All the other components are kind of abstracted away from us. Okay, and what this term abstracted means is that we don't have to think about them while we're writing code. Okay, all we have to think about is memory, because that's where our data lives. And data is the topic of our next lecture.